Well, this video we're going to talk about pressure. We're in the gas law unit, and we've talked about how gases can be described best by four properties: pressure, temperature, volume, and the number of moles, the number of particles. So I want to take this video just to address what is pressure. Those of you who haven't had pressure or learned pressure in physics, it may be a new concept to you and not really understandable. So this will be a longer video because we're actually going to watch a few YouTube clips as we go through it. So hang in there with me. At the end of this, we'll do a few pressure conversions, and I'll show you how to set those up. So first of all, what is pressure? Pressure is defined in physics as the force applied to something over or divided by the area that it's on. And in this first illustration, you see that we have this blue, wall piece of something, and this rectangular block is being applied, pushed against this blue object. But the interaction between the two objects is only equal to the cross-sectional area of the very end, that square there. So that's the contact area. And how hard you push on this block against the blue thing here determines the pressure. If you want to increase the pressure a lot and say puncture a hole through this blue thing, then you would want to make the area very small, like say the tip of an ice pick or a knife. But the broader this gets, the weaker the pressure applied is. So force and pressure for a lot of you may seem like the same thing, but they are different. It's force over area for pressure. Now here's another illustration here that many of you will probably understand. This is the difference in heel size. I'm going to attach this particular video in the Google Classroom posting for this lesson, and watch this. This is just a British TV show, kind of like Shark Tank or whatever, where a lady is trying to pitch her idea of expanding the side, a little tip that makes the heel bigger. So watch that if you want. But the concept here is that for women who wear these larger heeled shoes, walking is fairly normal. Not quite normal, but fairly normal. But as you go to the taller heels with the more pointy ends on them, walking becomes increasingly difficult, especially walking across bare ground. If it's muddy, it's even worse, or wet. And the reason is, while a person's weight doesn't change, their mass doesn't change, the pressure is constantly changing as you change these shoes, because the force is distributed on the green shoe here over a larger area. So there's not quite as much pressure. Whereas in the pink shoe, that same force is being applied to a very tiny. And you can see graphically here 100 square centimeters compared to 100 square millimeters compared to 1600 square millimeters. And the difference in pressure, if you plug these numbers into the equation, give you a vastly different pressure. 500 grams per cubic millimeter versus 31.25 grams per cubic millimeter. The particle model helps explain to us exactly what creates pressure in terms of gases. Now, we're not talking about liquids and solids because it's a slightly different phenomenon. It's related, but slightly different. So we're talking about just gases here. The kinetic molecular theory told us already that gas molecules are in constant random motion, so they're always zipping around. And when a gas molecule collides with something, we talked about the collisions being elastic, which means no energy is lost. That's fine, we're not going to change that. But let's also acknowledge the fact that when this, look over here in the picture, one of these speeding orange balls hits the surface of the wall or container, whatever this is, that it's going to exert a force on it. And that force that's exerted If you multiply or divide that by the surface area of the particle hitting it, that is what actually creates pressure. And these collisions are happening millions or billions collisions per second inside of a balloon or whatever. They're happening all the time. So it's a fairly constant. In actuality, pressure is never 100% constant because the number of collisions fluctuates slightly, but it's a very tiny difference, one that's imperceptible to your senses. As we talk about gases and gas pressure, what we're really concerned about is, if it's in a balloon, it's one thing, because the gases inside the balloon are creating an internal pressure. But we are also always surrounded by an atmosphere, an ocean of gas that we breathe all the time. And the atmosphere always exerts a pressure on us. So any kind of chemistry we do where gases are created and we're looking at gas particles, we have to kind of factor out the effect of the air pressure around us. So I have a couple of, this illustration here on the bottom left illustrates what air pressure is. There is a column of air from the ground all the way up to the absolute tip of outer space. And if you think about how many gas particles are there due to gravity, there's always more toward the bottom, toward the center of the earth, than there are at the top. Gas particles have a mass, so they are affected by gravity. So there's more gas particles at the bottom than there are at the top. But if you take the mass of the entire column here, and let's, for the sake of argument, assume this is a 1 square meter round or rectangular column, and you took the mass of every particle in this column all the way up to the edge of outer space, found the weight of that, and then divided it by 1 square meter, that would be atmospheric pressure in pascals. So that is very important. Now, if you look at the balloon picture, you can see here we have helium, and inside the balloon, the helium is bouncing around, as I showed you earlier, and colliding with the walls of the balloon, and it's pushing outward. What keeps the balloon from popping? Well, atmospheric pressure is the answer, because there are also oxygens and nitrogens and carbon dioxides and the things that we breathe also constantly bouncing around on the outside, hitting the balloon and pushing it back in. As you're blowing up a balloon, you are increasing the pressure, and so the balloon has a greater internal pressure than external, and the balloon as a result gets bigger. But as you allow it to come to an equilibrium, then you will have equilibrated or equal pressures inside and out. But there's always going to be more pressure inside the balloon, right? Because if you had less pressure, the balloon would just float up. So I don't want to confuse you with density issues as well as pressure issues, but there's more pressure inside of a balloon because if you pop it, stick a pin in it, all that pressure forces the gas out and it bursts the balloon. So there's always more pressure inside a balloon when you blow it up. But if it weren't for the atmospheric pressure pushing back in on the balloon, then every balloon you ever blew up would just go into its largest size possible and explode. That's what happens in science fiction movies when you see people or creatures being sucked into the vacuum of outer space. There's no atmospheric pressure to push back. And so they sometimes show those bodies ballooning out and then eventually exploding. There's a good scene of that in Alien, what is that? Alien 2 maybe? Or Alien Resurrection, Alien 3, I forget. Those of you who are science fiction fans can go find some of that stuff. All right, we are going to watch these two videos, so bear with me. The one on the left, we'll start with a classic chemistry demonstration. I'm sure many of you have seen this before.
This is two different levels of the experiment. have you ever tried to crush a can? You know, you get a soda can like this and you go, hey, that could hurt your hand after a while. You know, you do that enough. So why not just use this method, all right?
We need a device.
All right, so here's what happens. I have 3 soda cans that are empty, except for a little bit of water in the bottom. So I'm boiling some water in the bottom. See it kind of coming off here?
Yes.
Put your glasses on. So here's what we're going to do. Now that it's boiling, the water molecules have expanded and pushed all the air out. So here's the cool thing, is if we take this now, and I'm going to have you reach over, you're going to pick up the can, and then you're going to turn it upside down and seal it over the water. And I want you to watch what happens. Okay? All right. Insurance is paid up, is that right? So careful that one, grab that one. Turn it over. Turn it over.
Oh!
Nice! Isn't that beautiful?
Look at that. How good is that?
It's not literally, it's the air pressure. All right, so we want to focus on the bottle of water. We'll do it again.
Okay, as you can see in that video, atmospheric pressure is quite substantial. There's a lot of mass of air going up to the edge of outer space. So if you remove the internal pressure, like say of a balloon, its contents, or in this case, the air inside of a can, if you remove that, then the atmospheric pressure is enough to just absolutely crush it. What I would like you to do now is hit pause and go to your Google Classroom post, and I'd like you to watch the link to this video here on the right. It's going to go through the explanation of what's going on. Actually, I just changed my mind. This link will be there, but let's go ahead and watch it. I'm scared many of you won't hit pause and do it.
So we have an open can here, and the air, the atmosphere that's being pulled down by the gravity of the Earth is pushing on the outside of the can. But since this is an open can, the air inside, that same air being pulled down by the Earth's gravity, is pushing out. And then we have this kind of equilibrium here where nothing happens to the can. Let's think about those molecules inside of the can and what they're doing. So we have molecules of air, the red are oxygen, blue nitrogen, there's some argon, carbon dioxide, and water vapor. And as they move around, when they're hitting the side of the can, they're creating pressure. That's the air pressure. And that's pushing on the can from the inside. Of course, on the outside, we have the exact same pressure, and that's pushing on the can. Every time those molecules collide with the can, they create pressure as well. So let's think about liquid water. We put a little bit of water in the can, and it sits at the bottom of the can, and then we have the air above it with those gas molecules moving around. But if we start heating those water molecules, so here we have, as a liquid, these molecules are moving around, but they're pretty much staying together. They're not getting too far apart. If we raise the temperature up, it will change from a liquid into a gas, and the water molecules will spread out. When they do that, they'll push all of those air molecules out, and all we'll have inside of the can is water vapor. Let's see that happen. The temperature increases. You can see the water molecules are spreading out, and they'll force the air out of the can, leaving just water vapor in the can. So now we flip the can over, put it in water. That seals the top, so no air can get in, and we cool the can. And all that gas, that water vapor in there, changes back to a liquid very quickly. That's important because as a gas, the water molecules were hitting the side of the container and creating pressure. We still have air on the outside, molecules hitting the side of the container, creating pressure, but on the inside, we don't have the gas anymore. We have a vacuum because we've sealed the top when we turn the can over. And because of that, air pressure on the outside crushes the can.
So hopefully that gave you a good idea of what pressure is and then what atmospheric pressure is, because it's very important for us to negotiate that working chemical reaction. Well, how do we measure pressure? The old ways to measure pressure were a barometer. Of course, we still have barometers today, but we could also use pressure gauges. Pressure gauges do the similar thing, different mechanical apparatus, but they still give us pressure calculations. But the old barometers, where a lot of our pressure units came from, work very similar to the idea of the inverted can. You see here in this picture that I have some mercury. That's why it's kind of silvery here. Mercury is a liquid. And we've inverted a tube here. So when we do that, there's a vacuum at the very top. So this is actually totally empty up around here. There's no particles of anything. And then the atmospheric pressure does its job. It pushes down, contacts, collides with the surface of the mercury, creates a force, a pressure, and it pushes the mercury down, and then it's looking for an escape. And the escape is up here where there's nothing, there's no forces. So the mercury is forced up the tube until it generates a little bit of, it goes up until the weight of this column of mercury equals the force of the atmosphere pushing down. Okay, when those two are equal, we take this reading and see how high the column is. And at normal sea level, that's 760 millimeters. That's how high the mercury will be pushed by atmospheric pressure. That's the first barometer developed by Torricelli. And so he had a unit named after him, the torr. And there's another unit related to that, the millimeter of mercury. And on the right, you can see there are several other units of pressure that we're going to use. We're going to have the SI units, Pascal, and because a Pascal is so very small, that's the 1 Newton per meter squared. That's very small. And so therefore, kilopascals are more commonly used. We also have the atmosphere, which is the most common unit we're going to use for our calculations. That's simply because we say atmospheric pressure is just a 1, and that makes calculations a lot easier. We have the millimeter of mercury. Notice that the millimeter of mercury and the torr are about the same value. That makes a lot of sense if you know the history behind Torricelli and building the barometer. In the U.S., we also use PSI, pounds per square inch. 14.7 is atmospheric pressure in that particular unit. Those of you who've ever filled up soccer balls, volleyballs, basketballs, footballs, and the pressure gauges, or filled up a tire when you go to the gas station and you have to air up a tire. Those gauges read out like 28, 35. Those are PSIs. And then we have the bar, which is very similar to the atmosphere. We don't really use bar much. The only place I can think of you commonly see it is in your weather reports. For some reason, meteorologists still like to use bars, especially when reporting hurricane pressures that are typically expressed in millibars. So look for that in the upcoming summer. All right, so that's the nuts and bolts of pressure. Let's go to our practice and let me show you how to use these units and these atmospheric values to do pressure conversions.